Dear colleagues, we are from University of Oran 1, Ahmed bin Bella, Oran, Algeria. The presentation is on meal solutions for a stochastic partial differential equation with noise. We divide our presentation on three parts. In the first one, we introduce our problem. In the second part, we give some notion and certain important preliminaries. In the last part, we present our main result based on the well-known Sadowski fixed point theorem. We are interested in the existence of solution of the following nonlinear fractional differential equation subject to the initial value in 2 and the directly boundary condition in 3. The function u depends on x and t represents the velocity field of the fluid. The term GUWT describes a state U in a separable real Hilbert space, dependent random noise, where WT is a FT adapted Wiener process. The operator delta is the Laplacian, and the capital derivative of function u of order alpha respect to t is defined in equation 4. Let the filtered probability space omega f ft p and the operator a is the negative Laplacian minus delta, which is self-adjoint. And we define the domain of the fractional power h sigma. Then we can rewrite the equations 1, 2, and 3 as follows in the abstract form in 5. And we have L02, the space of Holder-Schmidt operators. Now we give some preliminaries lemma and the definition of milled solution. The following lemma that we need it concern the operator A nu. To estimate the stochastic integrals, we have lemma 2, which contain the Burkholder-Davis-Gondis inequality, when the letter E denotes the expectation. In the next, we give the definition of milled solution U for our time fractional stochastic equation 5 as follows, where E alpha and E alpha alpha are the generalized Metag-Leffler operators, where their expressions contains the analytic semigroup T and the Maynard right type function zeta alpha. The property of the function zeta alpha is presented in lemma 2.3, and the properties of the linear operators E alpha alpha are presented in lemma 2-4. In this part, we present our main results on the existence of the Mills solutions for the problem 5. We define the space K and we make 5 hypotheses. In each one, A is the infinitesimal generator of the semigroup TT and E alpha is compact. In H2, the continuous function G satisfies the Lipschitz-Greu conditions. The third hypothesis, H3, concern the initial value U0. In H4, we have H is continuous and satisfies the following inequalities. In definition 3.1, we present the Kuratowski measure of the non-compactness of the subset C. Definition 3.2 concerns the condensing MAP. If we have two operators that G1 is a contraction and G2 is compact, the sum G1 plus G2 is K set contraction that we have in lemma 3.1. Our main result is based on the following fixed point D2 Sadowski. If Y is a convex, bounded and closed subset in a Banach space, and we have a MAP phi condensing, then phi has a fixed point. In order to prove this result, we need the following lemma. If condition H1 and H2 hold, the MAP phi1 is continuous and is in K into itself, that we have in lemma 3.2. By the same hypothesis in previous lemma, we have phi2 a continuous MAP and MAPs and K into itself. In lemma 3.4, assume that H1 and H4 hold, then phi3 is continuous and MAPs K into itself. In lemma 3.4, assume that H1 and H4 hold, then phi3 is continuous and MAPs K into itself. In lemma 3.5, under satisfaction of hypothesis H1 and H2, the expectation E satisfying the following inequality. We define the MAP F and we decompose it as F equal F1 plus F2, where F1 and F2 defined in the cycle. In lemma 3.6 characterizes the strong continuity of the operator F2, and in lemma 3.7 we have F2 uniformly bounded. By the satisfaction of the same hypothesis in the previous lemma, we have f2 is equicontinuous in lemma 3.8. In the last lemma 3.9, assume the condition h1 and h2 hold. Then f maps k into itself. We divide the proof of this lemma in 3 steps. In the first one, we prove the set of all u in K satisfies u equal lambda fu is bounded. In step 2, we prove that f is continuous. In the last step, we decompose f as f equal f1 plus f2, where f1 and f2 definite above. Then we have f has a fixed point, which is a middle solution of the equation 1, 2, and 3. Thank you.